Good morning. My name is Brendan McGinty. I'm part of the Center for AI Innovation, and we host this weekly seminar series. And a couple of reminders that for questions during the seminar, please queue them up in chat, and I will queue them up at the end of the presentation. We should have some time at the end. We have the full hour. The recording, which this is being recorded, will be posted on our website, ai.ncsa.illinois.edu, in a few days. We have all of the other seminar series recordings available on that site. Very interesting series. So let's go ahead and get started with today's. We are honored to have Dr. Yogatheesan Varatharajah. Yoga received his bachelor's degree in 2013 at the University of Moratuwa in Sri Lanka, and his MS in 2015, PhD in 2020 from the University of Illinois at Urbana-Champaign in electrical and computer engineering. He was a recipient of an inaugural Mayo Clinic Illinois Alliance Fellowship, a Wordbased Computer Engineering Fellowship, and an American Epilepsy Society Young Investigator Award. He's currently a research assistant professor in the Department of Bioengineering at UIUC with secondary affiliations with the Department of ECE, Electrical and Computer Engineering, the Mayo Clinic Neurology, and National Center for Supercomputing Applications, NCSA. His research is funded by the NSF, National Science Foundation, and the Mayo Clinic Artificial Intelligence and Neurology program. Yoga, thank you so much for your time and being here today. The virtual floor is yours.
Thanks, Brandon, for the kind introduction. And thanks, Vlad, for having me here. And yeah, thanks everyone for joining. All right, so I'll be talking about my work on domain-guided machine learning for health analytics. As Brandon mentioned, I'm a research assistant professor in bioengineering, and I'm also a visiting scientist at the Mayo Clinic. So my work mostly focuses on machine learning applied to health analytics. And before we go into like the specific projects that I'll be talking about, I wanted to briefly introduce what I mean by domain-guided machine learning. And you may have seen this famous graph talking about the importance of deep learning when we have large amounts of data. And classically, we had machine learning methods which were very popular, but then recently, deep learning has taken over the entire field, especially because of the availability of large amounts of data. But really, this should be labeled like this. It's not just large amounts of data; it's large amounts of labeled data. And in most of health related machine learning projects, what we encounter is this low labeled data regime. So, in health, the problem is when we go and how do we generate this labeled data is we, experts especially, they have to go and annotate these records saying, okay, this is a particular class and this is another class and so on. And, unless, except for certain areas like imaging where there's large amounts of data and labels available, most of the problems in healthcare, they fall in this low labeled data regime. And we have to find ways to boost the performance of machine learning methods. So even with this low labeled data scenario, so that, we can match the expectations compared to like deep learning methods that that we get when we apply to like large amounts of data. So how do we do that? Is one of the ways that we have been using is domain-guided machine learning. So what this means is that instead of relying just on labeled data, can we use the expert domain knowledge that experts have gathered over years of training? Can we use them to design models that somehow capture the knowledge that the experts have, and then in addition, we'll use the available data to as complementary means of supervision. And then by this way, we will be able to improve the accuracy beyond what is achievable with the low label data sets. So that's what I mean by domain-guided machine learning. And then you may have also heard of this term self-supervision, which is recently becoming popular. So that's another way to deal with this. But there, the assumption is that in addition to a small amount of labeled data, we also have large amounts of unlabeled data. And then how do we use them to improve the performance? So we'll see how we can also use domain knowledge to guide self-supervision in a few examples. So with that, my and my research group's focus is on using domain guided models to address problems related to neurological diseases. So we work with measurements that come from the brain, and how can we use these domain guided models to extract some useful information that can be useful in clinical practice, mainly addressing questions like, can we predict something before they happen? Can we help with surgery, and so on and so forth? And the diseases I focus on are epilepsy and Alzheimer's disease primarily, and the types of data we work with are electroencephalography or EEG, so polysomnography or PSG, and recently we have started working on clinical text also. And this all wouldn't be possible without collaborations with the clinical folks. And I primarily work extensively collaborate with the Department of Neurology at Mayo Clinic. And recently we have also started working with the Cleveland Clinic and local partners like OSF and CAII. And finally, before we talk about the projects, I wanted to also introduce the specific data that I'll be working on. I'll be presenting about, which which is kind of different from most of the machine learning type data sets. So I wanted to briefly introduce that. So the electroencephalography or EEG is time series type data where we have multiple sensors on the head or in the brain. So that will distinguish this non-invasive versus invasive EEG. And then using these multiple sensors, we measure the electrical activity that happens in the brain, and that can help with diagnosing certain diseases and also with treatments and so on. So these different lines, they are called channels. So they represent individual sensors that are placed on the head. So the scalp EEG is on the head, and the intracranial EEG is like directly on the surface of the brain. It's also known as electrocorticography. So these are the types of data that I'll be talking about today. And the difference between scalp and intracranial EEG are basically, because we are measuring on the head, some of the high frequency activity won't propagate to the head. So therefore, the scalp EEG is, or intracranial EEG will have more high frequency content compared to scalp EEG. So that's the only difference. But then, you also have to remember intracranial means you have to open up the skull to put these sensors on the brain. So that's more cumbersome compared to scalp EEG. All right, so the outline of the talk today. So I'll be primarily talking about two projects. One is localizing brain regions for epilepsy surgery, where we used a domain-guided graphical model. This is mostly using expert knowledge to define a graphical model using which we can infer which parts of the brain are causing seizures so that we can remove them in a surgery. So that's the first one. And then the second one, we'll be talking about an EEG-based diagnosis of neurological diseases using a domain-guided graph neural network. Here we'll be using a graph-based CNN to diagnose neurological diseases at the earliest possible time using EEG. And then finally, I'll be talking about my two recent works on domain-guided self-supervised learning, briefly, with time permitting. Okay, so let's start. So the first work is on localizing brain regions for epilepsy surgery. So I want to briefly introduce the problem before I talk about the method. So the epilepsy is a disease that is characterized by seizures, and it affects about 70 to 80 million people around the world. And most of them are, they achieve good control of their seizures with medication, but then roughly like 30 to 40% have drug-resistant epilepsy, meaning they won't respond to medications. So one of the treatments that exists for those patients is epilepsy surgery, where we will remove the part of the brain that causes seizures. And how this happens is the patients, they get admitted to the hospital, and we put these intracranial EEG sensors on their brain, and then we monitor these patients for several days to record some seizures. And based on the origin of the seizures, the epileptologist can manually go and look at these EEG data during the time of the seizure, and then they can say, okay, these sensors are where the seizures are originating. So, if you go and look at the brain, we can see where the sensors are located. So, they can then remove that part of the brain. So, this, as you can see, it takes a lot of time, and there is also a manual component. You have to manually locate first in time where the seizure is, and then spatially you have to go and localize the part of the brain that's causing seizures. So there is a lot of moving parts. So as you can see here, so this is example data. So this is the EEG when there is no seizure, and then this is during a seizure. So you can see it's a big difference there. But the problem is that the seizures may not occur immediately. So you may have to wait for several days before seizures occur. And sometimes they may not occur in this day. So in that case, the whole experiment is pointless, and we have to do one more time to be able to localize the seizure generating brain region. So that becomes a problem. And what we wanted to do is, can we, without relying on seizures, can we look at this non-seizure data and then try to localize the part of the brain that causes seizures? So that's where we use this domain-guided graphical model. So to motivate how this is even possible, because the current practice is basically we have to look at seizures to do this. So this came from looking at the data in a different way. So here you have a recording of a seizure. So you can see that these middle sensors are kind of showing different type of activity compared to the rest of them. So if an epileptologist looks at this, then they will say, okay, these 3 particular sensors is where the earliest onset of the seizure is happening. So that's where that's the brain region causing seizures, and they can go and remove it. But what we looked at was the non-seizure data for the same sensors, and what we find is that there are some activity, although they're not as visible as the seizures, they're still different from the rest of the brain. So we may be able to use those activity to determine where the seizures are coming from. So this is what we did. And so what this means for the overall procedure is that currently, as I said, you have to first put the sensors on the brain, and then you have to monitor for several days. It could be a week, and to record seizures, and then you perform a surgery to remove that region. But what we can do with this is that, including the implantation and the surgery, and also we can localize this part of this seizure generating brain region with just 2 hours of non-seizure data. And then this overall procedure can now be incorporated into like one long surgical procedure, and that takes away a lot of time from the procedure, as well as difficulties with the manual interpretation and so on. So that's what we have done here. So Yeah, so I guess we'll be having questions in the chat and we'll look at them later. So I'll continue. How we identified the seizure related events from non-seizure data I'll motivate that here. So as I mentioned, we have to look for these specific events, which are called spikes in the EEG terminology. So we have to first find them. But finding these spikes or these events is very difficult. It says we have to use some sophisticated signal processing to do that. And most of the times we may be capturing non-spikes that that present as spikes. So we have to have ways to determine what is an actual spike that is related to the seizure and what is not. And to do that, we are going to use a couple of dependencies that we know from our domain experts. That's one is the spatial correlation. So if a few sensors are in this seizure generating region, we will see those spikes at the same time in those sensors. And then for the same sensors, we'll see these spikes at a more frequent rate compared to like other events which are not that frequent and they happen more at random. So can we use the spatial correlation and the repetitiveness of these events to determine which ones are actually relevant to our localization and which ones are not? So that's what we did. And so the overall process is like this. So we take like a 2-hour segment, as I mentioned, and then we divide them into like little epochs, and we detect these spikes using some signal processing methods. And then we apply like a graphical inference, which I'll talk about in the next slide. And using that, we can determine the events that are relevant to our localization. And then using that, we can estimate which of these channels are in the seizure generating region. So that's the overall procedure. And now how do we represent or how do we use this knowledge about the spatial and the temporal relationship of these events to determine which of these events are actually relevant to us? So, let's say we represent the state of a channel in a particular window as like 0 and 1, 1 meaning it's a relevant event and 0 meaning it's not. Then what other things can determine this is, one, the presence of events that we determine from the signal processing method. And then second, we have to look for other channels, especially the nearby channels, whether they have the same type of event. And third, we have to look for whether this particular channel had these events in the past and how frequent were they. So those things can influence the current state of the channel. And we can denote them using some notations. Here, Y and K means the current state of the channel, and X and K is the observation. So Y and L is the state of another channel or a nearby channel. And then Y1K up to Yn minus 1K are the previous states of the same channel. And we will represent those relationships using some functions which are known as factor functions. So in this case, we'll be using something called a factor graph, which basically means that you represent the relationships in a graph using specific functions. And then when you put them together, the entire probability density becomes the product of those individual factor functions. All right, so, and so as I said, these are the states and the events. And these are the definitions of these factor functions. So I won't go into too much detail here, but basically what this does is if there is an event or an abnormal event in that particular window, this function will say, okay, if there is an event, it's most likely that your state is also 1, meaning there is a relevant event. But that doesn't mean there cannot be a state where that is not a relevant event, but this will assign a higher value to the presence of an event. And then secondly, we have this spatial relationship. So this is inversely proportional to the distance between the channels. And if we have the distance and then we know the states of the individual channels, if they are similar, then or if they're nearby, then we make sure that the states are similar. And if they're not nearby, then states can be, arbitrary. And similarly, we have the temporal correlation where we say that, depending on the number of past events, if there are so many events in the past, we want to make sure that the current event is also an actual event that is relevant to the localization. If there aren't many events in the past, then this becomes a non-relevant event. All right, so that's how we define these functions. And then eventually what we do is we create a graph between all the channels in the in the data, and then this will be like a fully connected graph, and each channel will have an edge to another channel, and then that will be the relationship that determines that edge is basically defined by the spatial function that we talked about. And then they will also have this temporal function, which talks about the frequency of the events in the past. And then we'll also have the actual event that happened there. So the PDF of this graph is, as I said, is a product of the individual vector functions for each channel. And then since we have n number of channels or m number of channels, we'll just put them all together. That'll be our PDF. And then what we do is we replace these functions that we just defined in place of these specific events, specific functions, and then we can do some manipulations to find this is how we'll do inference once we have, let's say, certain xk, and then we know the phi omega n minus 1k, which is past events. And then once we have that, we can perform an inference on this particular formulation, and then we can determine the y case for each channels. And this is a combinatorial optimization problem, and we can solve this using a graph cut based approach. So this is how we perform inference. So what this will give us is that if you go back to the original, here. So here, the factor graph inference basically will take the i's, meaning the the event that was detected by the signal processing method, and then it will perform an inference to tell us whether that's relevant to our particular problem. And then once we have that, we can use a maximum likelihood estimation among all these different events that we determined. And then that basically means that we take an average of all the events, and then we determine whether, using a threshold, whether a particular channel is likely to be in the seizure generating region or not. Okay. All right, so here we have an example of the results. So you have to remember this is done per patient, meaning if we have, let's say, 30 channels in one patient's brain, we'll monitor those channels for an hour, and then we'll say, okay, out of these 30 channels, these 3 or 4 look like they may be in the seizure onset zone or seizure generating region, and the rest are not. So then we can go ahead and look at what was originally done for that patient, where the epileptologist went and looked at seizures and said, okay, these are the channels that are in the seizure onset zone, and then we can compare to generate these metrics of accuracy. So that's how we do this. So here, non-SOZ and SOZ means non-seizure onset zone and seizure onset zone. So those are the channels that are in the seizure onset zone and in the non-seizure onset zone. And we find that our method assigned probabilities, higher probabilities for those that are in the seizure onset zone versus those that are not. So it's encouraging, and then we can go ahead and plot an ROC curve for this particular patient. So this is not for all the patients. So, as I said, everything we do here is per patient. So for this patient, this is how the ROC curve looks like. And then we can also look at how our method, detected events or detected the region compared to the actual gold standard. So here we have the anatomical map of these sensors, and the yellow ones are the ones that were detected by the experts or the gold standard, and the red ones are the ones that were detected by us. So you can see there is a good match, but then we also find that we detected something that's like really out of the gold standard region. But I think that's primarily because there was a channel that was bad channel, meaning that was not properly in contact with the brain. So there was some, due to the way we do our inference, maybe we picked something that was not relevant to this. But the idea is that if you are able to visualize this on a 3D map like this, then you'll be able to see, okay, these are clustered together, so they will most likely be the seizure generating region compared to the other one, which is like really far away. And then we did this for about 80 patients who were treated at the Mayo Clinic, and we found that compared to all the previously existing methods, we performed significantly better. You can see, roughly like a 20% increase in the AUC using the model that we developed. So that's what we did here. And the overall idea is that, instead of waiting for days and weeks to be able to localize this, now we can do this with just 2 hours of data, which can also be included in like the long surgical procedure, which helps a lot with the time and cost of this procedure. So that's the first project. And then now I'm going to move to the next project. So here we'll be talking about, this work was done by my student Neeraj, and we worked on improving EEG-based diagnosis of neurological diseases with the graph neural network. So the idea here is, again, EEG, here we'll be talking about Scalp EEG. So before, so in the previous case, we saw an example where the intracranial EEG is used, but before all of that happens, the first line of diagnosis for epilepsy or most of the neurological diseases is a Scalp EEG. When a patient complains about something and they come to the hospital, we take a Scalp EEG, which takes about roughly 40 to 60 minutes. And they sit in a room and we put these sensors, and then we monitor their brain activity for roughly an hour. And then based on that, we can diagnose certain diseases. For example, if it's epilepsy, we can say it's epilepsy. But the more fine-grained diagnosis of like where the seizures are coming from and all that will have to happen from like a intracranial or long-term monitoring. But this is the first line diagnosis. And then what happens is, once we record this EEG, again, an expert will go and manually analyze this EEG and look for certain events that can indicate the potential for disease. And they can say, okay, there are some events, so it's an abnormal EEG, and then that can lead to treatments and other evaluations that can help with the treatments. But what happens if it's a normal EEG? Does that mean that the patient doesn't have any disease, or does that mean that we didn't capture anything? So that's really the question here. It turns out that roughly 50% of patient EEGs are labeled normal based on expert review. What this means is that when we record these EEGs, only 50% of the time we'll have an actual diagnosis of the disease. The rest 50%, we may not be able to diagnose anything, but if they come back for another evaluation later, or they do like a long-term study, then we'll find that the patient actually has a disease. We were just not able to make the diagnosis at the earliest possible time. This happens because of it's possible that we didn't record any useful events in that short duration of the EEG, or those events were not visible to the experts, so that they couldn't, they could not determine that this is an abnormal EEG. So that's the problem here. So what we did was we developed an automated method that can distinguish the patients, the EEGs that were determined as normal, but they came from a patient with a neurological disease, versus the EEGs of healthy patients. They don't have any diseases. So they also turn out to be normal, but then is there anything that can differentiate these two groups of EEGs? So that's what we did. And this work was presented at ML4H here, where it received an oral presentation. So the idea is what are we really looking for? Because they're, according to the expert, both these groups of EEGs are normal. But, what we did on our previous work, we found that there are some things that can be, there will be subtle abnormalities that we can capture using automated, like quantitative methods. And then, in addition to those, there are some features of these abnormalities that can help us further double down on those particular abnormalities. So one is the anatomical proximity. So if we find that one of these channels, so here the Scalp EEG is basically, it's different sensors on the head. I'm showing 8 here, but it can be, I think, roughly up to 20 channels, but they're all in the same locations for all the patients. So they're all uniform. So what I meant by the anatomical proximity is that, let's say we find there is something slightly abnormal in this particular channel, and we find that it's also showing in a nearby channel, it's very likely that will mean that it's an actual abnormality that can lead to an abnormal EEG diagnosis. So that's the anatomical proximity. And then the spectral similarity. So there is a normal pattern of the spectral activity of the EEG. And then there is some differences that you can see when you do a quantitative analysis. And then if that spectral pattern is different between, is the same between like nearby channels or between a pair of channels, then they're most likely representing the same type of abnormality. So those two things, what are the ones that drive our method, and how we represented this graph is basically we have these different sensors, and we can represent the relationship between each of these sensors using first the anatomical proximity and then the spectral similarity. And so we call them the spatial and the functional connectivity. So the spatial connectivity is basically the distance between the two sensors. And then the spectral or the functional connectivity is basically the coherence between the activities of those sensors in the spectral domain. And then using that, assuming we represent the features or the data that's coming from a channel using a set of features, then we can form this graph with edges defined in this particular way. We have the spatial and the functional. We just use like a simple addition of those two, and that will determine the connectivity between the two sensors. And then we can use graph convolutions based on this graph definition. And then we'll get an embedding for each node. And then we'll use like a global pooling or some type of pooling operation to get the graph level graph level embedding, and that can be used for eventual classifications. So that's the overall idea here. And we evaluated this using a data set, including 208 healthy people, and then around 1,300 patients. And what we did was we took an EEG, and then we divided them into windows. And for each window, we extracted these power spectral features, and then we used our, the graph neural network that I described in the previous slide to assign a probability for being a healthy person versus a patient. So that's what we want to know. Although, according to the experts, these are all normal EEGs, can we differentiate patient from healthy people? So that's what we did here. And then, this gives us a probability for like each specific window. And then we take the entire EEG and then we accumulate all the probabilities for the windows. And then we get a subject level probability. And then that's what we can use to assign or calculate metrics. So what we found here is that we are able to perform significantly well. One finding is that even traditional or classical machine learning methods do well in this particular task. That's because we are doing in a quantitative way compared to an expert who is just visually looking at this. But when we use this graph neural network, we find that we can do significantly better even compared to the traditional machine learning methods. And to illustrate why this is the case, we have here, we are showing the initial features that we extracted from the EEG data, and then we can see that between healthy and the patients, there isn't a lot of difference between the features. But when we apply this graph embedding, we find that the graph embeddings are actually able to significantly separate these two groups, and that's why we are able to see this kind of a performance in differentiating them. So the idea, again, I just want to reiterate that the point is, these were all EEGs that were determined as normal by experts, and we are still able to differentiate healthy people from patients using those normal EEGs. And that can significantly impact the timeline of the diagnosis and also the treatments. And therefore, this is a very significant finding. And currently, we are extending this method to a larger number of EEGs at the Mayo Clinic, where we want to develop a tool that can actually assist experts with giving a label at the earliest possible time. So that's that work. And now I want to briefly talk about a couple of projects that we have been recently doing. One is based on self-supervised learning. So I mentioned this before. The idea of self-supervised learning is that even if you have very small amount of labeled data, but if you have large amounts of unlabeled data, what you can do is you can use the unlabeled data first and generate like a feature extractor, which will be trained using labels that are derived from the data. We don't need an expert to come and tell us what the labels are, but we'll look for some type of structure that is within the data, and then we'll use that to train this model, and then we'll take that model and then fine tune it on another small data set which has labels for the task that we are interested in. So that's the overall idea. And for EEG, what are the types of self-supervisions that we can do? One is that we know for at least for healthy people, the brain activity in the right and the left hemisphere, they should look somewhat similar. So we can use that to train like a base model, and then we can also measure the behavioral states of the brain activity over time, like whether you are awake or whether you are sleeping, or what stage of sleep are you in and so on and so forth, we can measure from the data itself. We don't need to, if you want actual labels for that, we need an expert to come and look at that and annotate, but we can also get very coarse measures from the data. And then we can use that to train a model. And then we also know that, there are some changes that happen over age in EEG. So we can use the age of the patient to train a feature extractor. So that will reflect the age-related changes that happen in EEG. So these are some of the things that we can use to train a general feature extractor for EEG data. And we developed something like this. Here we used a ResNet backbone, and we trained a general feature extractor for EEG data using these 3 different self-supervision tasks. And we used a very large EEG corpus to first train this feature extractor. And then we used that feature extractor on a smaller data set with labels to fine tune. And then we were able to predict some useful labels using this trained model. And we found that doing this significantly outperforms traditional methods, which train only on the label data set. So that's the idea here. And this work is in submission currently at ML4H. So that's one work. And then the other work is on clinical text. So here we wanted to analyze EEG reports. So another way to extract labels for EEG data is to look at the reports, which are kind of in natural free text format, but can we extract certain labels which can help us with training models. So that's what we wanted to do here. So the idea is we want to find some segments or phrases in these reports that are important for a particular classification. So here we wanted to say whether the patient has epilepsy, or the patient has an abnormal EEG, or the patient the type of the seizure the patient is having. So can we extract this information from the report itself? And to do that, we need to find some phrases that are relevant, because there is 100 sentences in the report. Not everything may be relevant to the particular label that we're looking for, but we need to identify a few phrases that are relevant. So that's the task here. And this was work done by Sam. So here what we did was there are these word-based models that were trained on clinical text data. And they are very good at finding relevant phrases from large amount of text data that are relevant to a particular problem. What we are doing is we are basically taking that model and then fine-tuning that model on the large EEG report database that we have. And then that's basically fine-tuning or adapting that model to our domain. And then we use that to identify some relevant features from the reports that can help us with classifying these labels. So this work is also, this has been accepted at MLHC and also at SPMB. So I didn't go into much detail of on these projects, but in the interest of time, I wanted to briefly talk about them. And finally, I just want to acknowledge the students who have done some of this work. So Neeraj, Sam, John, and Teja are my students who have worked on these projects. And I also want to acknowledge my collaborators, Professor Ravi Iyer, Dr. Greg Worrell, Ben Brinkman, Dave Jones, Prashanthi Vemuri, and Sue Herman. Professor Iyer is at UIUC, 4 of them are at Mayo, and then Sue Herman is at Barrow. And then I also want to thank the funding sources, NSF, Mayo Clinic, and also the Jump Arches Foundation. So with that, finally, I just want to do a little marketing. So our department has been working on this AI in Medicine certificate program. So we have, this is targeted for clinicians who want to understand how to use AI in their practice. So this is, this is not very technical, but it's a very high-level overview of the AI methods and some applications. And then we also have access to experts. So if you have any questions, or if you want to work on an AI project, you can talk to experts in the field. So this is a 6-week course, but you can, it's self-paced. Once you sign in or register, you'll have access to the material for about 6 months, and then you can review them at your own pace. And this was jointly developed by the Department of Bioengineering, the CAII College of Medicine, and the College of Veterinary Medicine at U of I. And there's a link. You can go and look at what is available in the course and register. And I think we also have discounts for U of I students and employees, also CARL and OSF employees. So feel free to take a look at this, and please reach out to us if you have any questions about this. All right, with that, I conclude my talk, and I'm happy to take any questions.
Yoga, fascinating talk. As someone who grew up around epilepsy, I wish some of this research was available years ago. And just the use of EEG. The first question in the chat from Jahui, I'll just read, and I'll go one piece at a time. There are 4 parts to it. So regarding the project of using EEG to characterize neurological disorder, 1, are these EEG recordings from various patients?
Right. So in the first, so these are all from various patients. But in the first case, I think, as mentioned, we'll be looking at only one patient's EEG at a time to determine which sensors are in the seizure onset zone, versus in the second case, we are looking at a subject level classification. So yeah, these are from different patients, but the classification happens at a different level. Right.
Second part is, when you train and test graph CNN on these recordings, did you specifically separate pools with no overlap on subjects, or they are pooled together and there's overlap of subject in training and testing?
Right. So that's a good point. We did, in fact, separate. So, in the training, we didn't share the epochs of the same subject in training and testing, so on. So we separated these so that we don't have leakage of the same data in the testing procedure. Yeah.
The third part, how's the generalizability on different patients, since the medical data are very subject biased?
Right. Yeah, so that's a good question, and there's not a lot of convincing answer to that. But what we are trying to do here is, again, a more generalizable approach. And one advantage we have is that all the EEG data from these patients, they have the same structure, meaning they're at the same positions of the on the head. So that gives us some basis to compare different EEGs from different patients. But beyond that, how these EEGs are different across patients is a different question that we did not try to answer here. But that's a good point, though. Yeah.
Excellent. And then the final part of it is there any pre-processing that you use to tackle the problems above?
Right. Yeah. So yeah, that's a good point too. So by doing some sort of pre-processing, we can bring all the EEGs to like a similar space so that we can compare them. So one of them is to like normalize the power of the EEG so that all the EEGs have the same power range. So that's one aspect we did. And then you can also like center the data so that they're all in the same level. So yeah, so those things we have done. Yeah.
Excellent. Yoga Vlad asks, how far is your new EEG analysis method from a practical use in clinical diagnosis?
Right. So yeah, as I mentioned, that's a good question. And as I mentioned, we are currently working with the Mayo Clinic Neurology AI program to translate this into practice. So one of the things that we are doing is we want to first know given this, our finding, will that be useful when we actually implement in practice? So we want to know if we give this output to an expert while they're reviewing an EEG, does that improve the patient care? Can that help with diagnosing the disease earlier? Does the patient get a better outcome? So we are currently in the process of evaluating that. I think once that happens, then this will be used routinely in the clinic. So that's what we're working on.
And I'm curious, at the end of the description of your first project, you talked about something that we love when we talk about the confluence of AI in leveraging high performance computing. And you talked about going from days and weeks to 2 hours in a run. What did that look like? What was the environment that you used? What were some of the tools that you used to achieve that optimization?
Right. Yeah, that's a good point, actually. So, most of the savings in time that we obtained that from, looking at this problem from a different perspective. So, why that takes so much time is that we have to wait for seizures to occur, and they take a lot of time, days to weeks. But here we said we don't need to look for seizures. We can look at normal part of the data, and then we can still localize it. So that's where most of the saving comes from. But then in addition to that, again, when we record this data, this is like terabytes of data. So this, several days worth of data and multiple sensors, and the processing actually, when this happens, this takes like hours to days to actually run. So you can imagine if we were to do this in real time, this will require significant compute. And that's where I think, optimizations at a more granular, like a hardware level or at a software level may be beneficial here. And we'll be very happy to talk to you if there are people interested in looking at that.
Very good. I don't see any other. No, I see a couple of other questions coming. Actually, what do you think? And this is from Jahui again. What do you think is the advantage of using 1D/2D CNN for single multi-channel on raw data compared to graph CNN? Or what's the motivation of using a GCNN over a standard CNN? We'll start with that.
Right. Yeah. So that's a good point too. And I think there are approaches that look at 1D CNN for like a time domain convolution, and then 2D CNN. We have been looking at that, but the advantage of using a graph CNN here is basically that in a 2D CNN you assume that the individual channels, they're kind of independent. They're like we put them in a square, and then you assume, okay, they're these independent channels, but we know that there is some relationship between them. They're spatially, some channels may be spatially closer, some channels may be functionally closer. So how can we use this knowledge that we have to enforce that kind of a representation that in the representation that the model learns is what we are doing here. And we find that works better, significantly better, when we have not a lot of labeled data. But this may be relevant when we have so much data that we don't need to really enforce this requirement. But as I said, this is very relevant to the problems that we are working on. So that's why we did that.
And then Vlad asks, is it possible to generate EEG training data sets programmatically without actually collecting them from real patients? In other words, are there mathematical models for abnormal EEG?
Right. Yeah. That's a good question too. It's possible, but the physicians won't believe anything if we do it on synthetic data. That's the main issue there. But I agree that there has been works on generating synthetic data to train models, I think on X-ray and also MRI and so on. And then we can train models on the synthetic data and then go and apply that on real data. And it seems to boost performance. So that may be some direction we could look at. Yeah, good point.
Very good. Terrific questions. Thank you, everyone. I don't see any others in the chat, so we will give a couple minutes back. Yoga, thank you so much for your time today. We appreciate it. A fascinating talk. It will be on our website in a few days. We look forward to next week. Join us again then. Thank you so much and have a great rest of your day. Thank you.
All right. Thank you so much. Thanks, everyone, and thanks especially Brandon for moderating this discussion. All right. Great.
Pleasure. Thank you.